Okay, I think we can get started. Yeah, sorry, I couldn't switch on my video. I was in outside in workshop. Uh, yeah, thank you,
Eh,
Dr. Anna, for joining. Yeah, welcome everyone. Thank you for
Just
joining.
one minute. Let me just
Oh yeah,
resume the recording.
please start recording.
Okay, sir. You can go ahead now.
Great. Yeah, thank you, Priyank. Yeah. Welcome everyone. Thank you for joining IEEE Sensors Council Optical Sensors Cluster webinar series. This is webinar 7. Expert speaker Dr. Anna, thank you very much for your time and then delivering this talk. So this session is recorded and then made available through IEEE Sensors Council YouTube channel. And then if you missed past webinars, please go ahead and then I can watch whenever you want. Thank you, Dr. Anna, again for this opportunity. And then let me, before you start, I gonna read your biography. Uh, so Dr. Anna is a physicist by training, is Senior Research Associate of the National Research Council of Italy, CNR, at the Institute of Applied Physics, Nello Cara, which she joined in 1984. Her early work focused on designing and experimenting with fiber optic sensors and networks for physical and chemical parameter monitoring before expanding into optical spectroscopy-based sensing for environmental and industrial applications. So Dr. Anna current research focus on visible and near-infrared spectroscopy for food analysis, particularly in multi-component assessments of neutralical and safety indicators using a single light shot and multivariate spectral data processing. Her work has been supported by European and national research grants in applied optical sensing, and she holds multiple US and EU patents. She has been a visiting scientist at laboratories in Belgium, Ireland, and China, and serves as an expert evaluator, project reviewer, and advisor for international funding agencies. She's also a fellow of SPI. She was a member of the SPI board of directors for the from 2016 to 2018 in ITEM. Currently, she is a member at large of the IEEE Sensor Council, where she previously chaired the Diversity and Inclusion Committee. From 2017 to 2022, she was seconded to Brussels as a national expert at the European Research Council Executive Agency of the European Commission, contributing as scientific officer to the Systems and Communications Engineering, Condensed Matter Physics, and Synergy panels. So she has a very great profile, and then we are fortunate to have her, Dr. Hannah, today. Uh, Thank you, Dr. Anna, and please go ahead. Thank you.
Thank you very much, Nagesh, for the very nice presentation, and thanks to the Census Council for organizing these meetings, these webinars, particularly to Professor Carlos Ruiz Zamarreno, who is coordinating the optical sensor cluster. And in case you are interested to join this cluster, please contact me or contact him. And so we become even a bigger community. I'm from Italy. This is a view of my the area of research where my institute is located and where my lab are located are behind the airport. If by chance you cross Florence, please let me know, and we will be very pleased to welcome you in our labs. We are spectroscopists since the 2000. Spectroscopists in the visible and near infrared spectral region. We just shine light, and then we do absorption or fluorescence or Raman measurements, and we always combine with chemometrics to achieve a multi-component analysis. So the dream is to do a single spectroscopic measurement, to build a model with mathematics, and then to have a model for multi-component analytics. Before approaching food, which is now my main my main topic, the main topic of my group, we have worked extensively in the environmental sector for water monitoring, or industrial sector, for example, for monitoring the aging of lubricant oils, and also for monitoring the quality of wine during the, for example, during the production of port wine in Portugal. Then our dream is now to do a photonic tasting. That means probing food just by light, just a shot of light. You get the spectrum, then you process the spectrum with some reference data. And what you can do is a multi-component analysis for quality, for authenticity, and also for safety indicators. This is a green approach. Green is a word that is used and abused, but spectroscopy is really a green approach because you just use light and mathematics. You do not use any chemistry. Using chemistry means that you need to discharge and you need safety rules. Without any chemistry, you don't discharge anything. So it's really a green approach. What visible and near infrared spectroscopy has to offer for food analytics? The visible spectral range is very rich because all the dyes and pigments that make the food so colored and so beautiful have a reflection or absorption in the visible spectral range. Think of flavonoids or other phenol derivatives that are blue or towards the blue region, or carotenoids that are, for example, in tomato. The lycopene in tomato is orange, orange red, or the chlorophylls. But in addition to the visible spectral range, there is another very important range. It is the near infrared, up to 2500 nanometers, where the overtones and combinations of overtones of the carbon hydrogen, oxygen hydrogen, nitrogen hydrogen bonds lies. So it's very rich. Combining in many cases visible and near infrared, you have an entire fingerprinting of the food. Every components contribute with some or with the own spectrum, but it is the entire signature that you measure. The entire signature, okay, it is a fingerprint, but it lacks of selectivity. This is why you always need some mathematics to get rid of the information that you're looking for from the spectrum. Now it is the time of mathematics. It is the time of artificial intelligence. And if you ask me which is the best mathematics to use, I do not have an answer for that. The best mathematics to use is the one that works for building the model and is the one that works for verifying the model, for validating the model that you built. We are using chemometrics. We are using chemometrics since more than 20 years. So we have our own programs, we have our own software, although we are using also commercial software. But there are other examples in the literature using other type of machine learning, of other types of artificial neural networks or deep learning. So there is no rules for using mathematics, but the mathematics you use, make sure that you do not simply build a model, but you also verify your model in a validation phase. Let me see what the process that we use for extracting both qualitative and quantitative information from the spectrum. First of all, we start with a set of selected reference samples. And these samples must be selected accurately because they are the basis of the model that you're going to build. Then we measure the spectra, and simply from the spectra with an unsupervised action, we can reduce the dimensionality of the spectra, getting class identification, threshold, or also authentication. But if we want to do a quantitative analysis, we always need to have the reference analytical data of the selected samples. And in this case, combining the measured spectra with the analytical data, it is possible to have really a quantitative analysis. That means the concentration detection and also a multi-component analytics. Usually we get curves, linear curves like this. Very important is this, the parameter, that is the regression coefficient. The closer to 1, the better is the model. But not only the regression coefficient is important, also the spread of the data around the linear regression. Because in this case, the error is very little because the spread is very close to the straight line. But in this case, the model is very poor and there is not much to do. It is important to have selected very well the reference sample to cover all the range that you want to measure. And then whatever you get, you have to honestly declare whether you have an excellent or a poor data. But after building the model, very important is to do the validation phase. I would say that the validation data are even more important than the calibration ones. From now onwards, you will see spectra, you will see maps, clustering maps like this, and you will see also some calibration curves. Let me comment a bit about the route of spectroscopy, because many of you, I'm sure, saw in the lab all the spectrophotometers that are still working in many labs, but they are not practical for on-site applications. After that, and we are speaking of the 80s or even before, and after that in the 2000s, there were smaller components available on the market. And with smaller components, we were able to build smaller device and to take spectroscopy outside the lab. And after the 2010, there were available also handheld spectrometers, typical guns with inside all the components for spectroscopy, or system arranged like meters. And they were extremely useful to expand the use of spectroscopy for on-site and in the real world application. Now, the question is now, everyone has a mobile phone in the pocket, even more than one. The question is, can we use a mobile phone for spectroscopy? At the end of the day, the mobile phone has a source and has a detector. So in principle, at least for the visible spectral range, it could be used to make spectroscopy. But if you use the mobile phone alone, without any other component, what you get is an RGB response. So 3 bands only, slicing the visible optical spectrum with 3 bands overlapping. So this is not very much ideal, although with chemometries you can do much, but the spectroscopic resolution is really poor. There are examples, and we also have experimented gratings that you can clip on or you can put on the cover and slide on the camera to have a response not in 3 bands only, but the entire visible spectrum. But these were not very much practical. Actually, I'm not suggesting you to use systems like these. Other examples that have been proposed in the literature is to use special covers with special optical components. And these things are working better. The only problem is that what you do now for a cover, the cell phone model changed every week, and the cover now you cannot use as a cover for next model. So also these, although very well performing, also these I'm not considering very much useful for practical applications. The future that we have ahead is to have real spectrometers, not only in the visible, but also in the near infrared spectral range, integrated into the smartphones as additional cameras. The technology is there. There are many devices proposed in the literature, but not yet compatible, not yet offered as commercial products. What we can do now is to use the smartphone as a hub, like an octopus, connected Bluetooth with the mobile phone. So if you have something that connects to the mobile phone, you can scan your food or whatever you want to scan, get the spectrum, send to the mobile phone, and from the mobile phone to a cloud for data processing. And then from the cloud, you can get back the data on the mobile phone. This is very practical and a very nice configuration of doing spectroscopy with something that you have in your pocket. In on the market, that this is a list that devices that can be coupled to a mobile phone. In some cases, they operate in the visible spectral range. In other cases, they operated in the near infrared spectral range. And the difference is the detector used. If you are curious to have the entire overview of devices commercially available, I am suggesting you to read these very nice reviews that recently appeared in the literature. What I'm going to show you today, what I'm going to show you today is what we did with two devices. One is the SIO device. It was created by the Israeli company Consumer Physics, and it was the first that appeared connected by Bluetooth to a mobile phone, and we have used for several tests, not only in olive oil, but also for agri-food applications, not only food, also for agri-food applications, and more recently also for authentication purposes. The other device that I'm going to show you is the Spectroscopy. It is made by a company in the Netherlands. A very nice device also. I mean, this was our selection. I do not want to suggest you anything to buy, of course, but this is what we have selected for our use, and we were happy to use. So what I'm going to show you is what we did with these devices. Of course, in the literature, you're finding a lot of examples using all these devices, and every day, and not every day, but let's say every month or very frequently, there are also new devices appearing on the market. So we do not do benchmarking. There are papers that benchmarked devices to see what's better. I think that you have to start, if you want to do spectroscopy with something pocket-sized, you have to start with someone, the one that is more convenient for you, the cheapest or the smallest or whatever, and then continue with that one. The devices, both SIO and SpectraPod, and also some of the others, are particular. They are not using a grating for having the wavelength separation of the detected light. They are using filters. Filters mean that you slice the optical spectrum that you have measured with slices, and for every filter you get the integral, the integral of the light that the filter is filtering. So in practice, the spectrum is not a continuous spectrum, but it is a sort of pixels. From the pixels, in some cases, it is possible to reconstruct the spectrum if you have the transfer function of the filters. But so the approach is different. These devices, especially the pocket-sized devices, do not use a grating. They are using filters. Doesn't mean, of course, the spectroscopic resolution is smaller than the one obtained by a grating, but in many cases is more than enough. Let me start with the first device that we have used. This is the SIO. This is the spectroscopic range for 740 to 1070 nanometers. And these were the several models, several prototypes that were proposed before getting the final one that appeared in a Kickstarter campaign in 2013. It is covered by a lot of patents. We don't know what is inside, but some scientists disassembled, destroyed one, and saw that inside there is the light, that is this one, and then there is the detector chip. The detector chip is an array of 12 filters. On top of the filters, there is a mask for signal equalization. And there is also a series of micro lenses for the best coupling of to the detector. This is the old model. Now there is a new model that is mini. It is exactly the same. The heart is exactly the same. Simply they have improved the battery shelf life, and also they have created a different optical head, shielding a bit the environmental light. They are offering apps for specific application to measure the moisture of animal feed, to measure the quality of corn or the sugar of berries, of the fats in dairy products. But we have, and if you get one, you can have access to your own data and create your own app. And this is what we did. In the literature, you're finding more than 100 records that are discussing the results achieved with the SIO. We have tested with olive oil, with olive leaves, with tomato plants, with honey, and with carob molasses. And this is what I'm going to show you now. Olive oil. This is the transmission spectrum of different types of olive oil. We are addicted to olive oil. It is made in our region, and it is the best product of our region. If you come to Tuscany as a tourist, you can see fields of olive oils, very nice in our hills, and the product is very good, soaked with antioxidants, and it is the basis of the famous Mediterranean diet. So the entire spectrum of the olive oil is very wide, and there are several bands where you can see many differences. What the SIO measure is a very limited band, but in spite of that, in spite of the very limited band, it was possible to detect whether the oil was extra virgin or not, and it was also possible to detect the profile of fatty acids. This is a typical library of olive oils that we have collected in a couple of years, and we have included not only top quality extra virgin olive oils, but we have included also low quality olive oil, including pomace and lampante. We have created by our 3D printer a holder holding the SIO device in front of the vial, and we did a lot of measurements. The results of these measurements, simply by a principal component analysis, is that you can easily cluster the extra virgin and the non-extra virgin olive oil. And if we go a little bit farther with the calibration and validation set, we can see that the accuracy of distinguishing extra virgin and non-extra virgin olive oil is higher than 90%. But if you have extra virgin or non-extra virgin olive oil, should be declared by the producers. What the producers are very interested to do is to measure online during the olive oil production the fatty acids profile. Simply by the spectra and simply by a chemometric processing, we were able to distinguish and to, not only to distinguish, but to quantify, the concentration of polyunsaturated fatty acids. You see here the results that the regression coefficient is about 0.95 in calibration and 0.92 in validation, so very, very good. And we were able to quantify reasonably well the monounsaturated fatty acids. Again, these are the regression coefficients that are acceptable. And we were able to quantify, not as good as the other, but it's still a good quantification that can be used also to label the product, the saturated fatty acids. The producers of olive oil are curious to see also the presence of water because the olives are washed before, and there is always a little water that remains. And from this spectra, we were able to distinguish, we put a threshold in 0.05% in volume for water, and we were able to distinguish simply by a shot of light, simply by processing by chemometrics, this kind of spectra, we were able to distinguish this threshold with a very good accuracy, higher, nearly 97%. This is an application for food, for the final olive oil, but we can also have applications for the plant. Plants normally in our region are not watered. Watering is very expensive and the water is very scarce. Even in places where there are lakes and where there are water resources, it is difficult to water and the season is always dry. So we would like to see if and to what extent we can detect from the leaves if it is time to water or not. To have an app like this one that tells you, you shine the light on the leaves, you get the reflected light, and you have an app that tells you whether it is time to water or not the entire plantation. And this is what we did. We did many measurements during time. Unfortunately, this year we didn't have a very dry season, so we didn't measure really the water scarcity and the water stress, but we were able to build a very good model for measuring the water content in leaves with an accuracy better than 80%. Speaking again about plants, we joined the project with a producer of tomato and a producer of devices for tomato grown in-house. The question was, can we detect the infection by fungi, the fungi that are growing in the stem of the tomato plant, can we detect non-destructively without cutting the coating of the plant to see if it is gray, if the fungi starts or not? This is the same plant, the same stem, but part of the stem is healthy and the other part is infected by fungi. But so far, you could detect that only cutting the coating. So the question is it possible to do it non-destructively? Because the near-infrared light crosses the coating. It is going inside. So we can do a non-destructive testing simply measuring the reflectance spectrum with the device but coupled to the plant. And this is what we did. Other people did in the entire spectroscopic range. We did in this slide of spectroscopic range, and it was also very much effective. See the different spectra measured, these are converted into absorption, but consider that these are spectra. And with an accuracy better than 90%. So you can see how powerful is this device, little device, pocket-sized device, and how powerful it is, and how powerful is measuring, processing this spectra by chemometrics. Getting back to food, I want to show you an example an exercise that we recently did with honey. Honey can be made by different botanic origins, depending on where the flies the bees are getting the flowers. We had samples coming from chestnut, citrus, and eucalyptus. They were certified chestnut, citrus, eucalyptus. And the question was, can we distinguish the type of botanic origin simply by shining light on the product? And you see here the different spectra that if you process simply by a principal component analysis, which is the basis of chemometrics and the easiest way of using chemometrics, you see that you can easily distinguish the citrus and the eucalyptus and the chestnut. This was just as an exercise that shows you how near-infrared spectroscopy, even made by a pocket-sized device, can provide you very good and very interesting results. Another exercise that we did for authentication, we wanted to authenticate carob molasses. Carob molasses are made in the North Africa. We had a student from Lebanon. She took with us a lot of samples of carob molasses. And we also add we also added carob molasses from sugar cane, which is slightly different. These are the basic spectra of all the carob molasses and the sugar cane. You see some difference. And we have mixed with sucrose and fructose at solutions at different concentration, because this is the way that these products are adulterated, are made fake. Sugar and sucrose and fructose have a different cost rather than carob molasses. So it is much easy to adulterate them with sucrose or fructose solution rather than doing the real product. And these are the spectra that you get mixing mixing the original carob molasses with the sucrose or fructose. And we can also we can quantify from this spectra, we cannot tell you if it is fructose or glucose, but we can easily quantify the concentration of the adulterated syrup added with an extremely good regression coefficient in both validation and, in both model building and validation. Now, this is what we did with SIO. I told you that we have used another very nice device. It is totally different because you can connect, you can plug in to your computer or to the smartphone, but it does not need the cloud. I mean, you can get the data without the cloud, and you can process your data without sending the data to the cloud and giving them back. Because in some cases, some people do not want to be connected to a cloud, do not want to send the data to a cloud. Although it is safe, sending data to a cloud means to be traced. And some producers do not want to be traced, do not want to, I mean, they want to keep their own data. This is different as a technology. Here the technology was published. You can see here the papers that the technology refers to. And in practice, it is a stack of semiconductors. Every pixel, every detector includes the detector itself and the filter. And in this case, there are 16 filters spanning over a wider spectroscopic range. The new model This is an old model that we bought in 2023, and it covers the range from, let's say, 800 to 1700, but they are offering now a new chip, a new model that covers also the range in the visible. But at the end of the day, what you have is always a series of pixels. In this case, it is not possible, or it is too difficult to recover as a spectrum, and we just worked with pixels. Let me see what we did with an exercise, and that was requested by producers of flowers. Flowers made of different cereals, legumes, tubers, others. We had the collection of 47 flowers, and these are the related reflectance spectra that we have measured by this very little device. And we were curious to see if it is possible to detect the threshold of carbohydrates and the threshold for proteins. So we divided we divided our spectra into two groups: low carbs, high carbs, or low proteins and high proteins. And we were able to assign the right threshold with an accuracy of 93% in calibration, and for carbohydrates, and 82% for proteins, simply by a shot of light. Recently, at the beginning of this year at the Photonics West exhibition, I saw that this product, the SpectraPod by Mantispectra, is now produced in a smaller frame, and it can also be coupled directly to the mobile phone. This is a prototype that StellarNet built, simply 3D printing a case, connecting directly this spectrometer to a mobile phone. There are other examples that they are prototypes, or in many cases they are just ideas of coupling these little chips directly on the mobile phone. They will come soon. I'm sure that in a couple of years we will see not only concepts like those shown in this slide, but we will see really, it's just a matter of the production capacity and of cost of the device, but also the production capacity. These are concepts that have been proposed to couple directly the spectrometers or the spectral sensors as an additional eye of the mobile phone, to make spectroscopy available for everyone, to make spectroscopy in every pocket. There is the world of home appliances is pushing for the development of these devices integrated in home appliances. We have a study ongoing measuring the frying oil, the quality of frying oil in fryers, even in home appliances, domestic fryers. And there are also concepts of integrating these devices in smart fridges, for example, or in smart robot cleaner, so that the robot is understanding which kind of floor it is cleaning, whether wood or a moquette or a carpet or whatever. So this kind of devices are really, it's the last frontier. To couple them to home appliance is really the last frontier for them. There are now already done by 1/3. 1/3 is a nice company that would like to reduce the food waste, and for that they have they have produced an avocado scanner. I'm sure that when you buy the avocado, you taste it, you squeeze it to check if the ripening is okay, if it is too soft or too hard. In this case, simply with this kind of device that works in the near infrared and has a tablet that tells you the ripening stage. This is already in our supermarket. In the UK, in Bulgaria, in Belgium, and in the Netherlands, you are finding in the big distribution. What else? There are other devices this is another device that I saw at the Photonics West exhibition, other spectrometers that can be made compatible with the frame of a smartwatch or other pocket size spectrometer, but there are many others. I do not want to make, I mean, I don't, these are not my preferences. I simply something that I saw at exhibition that I attended. There is another very important area where these spectrometers can be used, and it is in agriculture, in robotic agriculture. The robots are already equipped by cameras to size and to see with the computer vision system to see what they are picking up. Equipping the robot with these kinds of sensors, especially for the near infrared, they can detect sugar. So, for example, for strawberry or for grapes, it is important to detect not only the color and the size, but also if the ripening is enough, if the ripening in terms of sugar is enough, particularly for grapes. In many cases, the grapes seem to be ready for being picking up, but they are not enough sweet. So maybe it's better to wait other days to get the right level of sugar of the ripening. I discussed with you today examples of spectrometers for food and something in agri-food, but if you are curious to see what photonics has to offer for the entire world of agri-food, this is a roadmap that we recently published with the colleagues Lynn Smithers and Francesca Venturini, and there are many authors, there are 32 or 33 chapters and many authors that contributed to this roadmap. So please have a look to this, and so we have an entire figure of what photonics, not necessarily pocket sizes, also big devices, but very straightforward applied to the agri-food sector. And if you are in contact with companies that, or yourself, that would like to have a photonic answer to a particular industrial question, consider that there is this Photon Hub project. It is funded by the European Commission. It will become another project, Photon Hub Factory, supporting projects for industrial application. The part of the cost is paid by the European Commission, and the industry is paying only a part of the entire cost. So with that, I think that I told you what I wanted to tell you, and I thank you very much for your kind attention. Thanks to the organizers for the invitation, and thanks to all of you for listening and for your questions, if any. Whatever you have to ask, if you want to come and work with us, these are our emails. You can contact us at any time. We will be very happy, and we are keen to host you and to do experiments together. So thank you very much. I think that I can stop my sharing and come back to you.
Great. Yeah, thank you, Dr. Anna. Yeah, it was a great talk. Yeah, like good to see lots of applications in olive oil, tomato plants, and honey classification, agriculture. Yeah, good to see lots of applications of spectroscopy. Yeah, thank you very much. Yes, it was a great talk. Yeah. If anyone have questions, yeah, please unmute yourself or type your question in the chat box, please.
If you don't have questions now, but maybe tomorrow or in a month or in a year, I'm writing here my email. I'm writing in the chat my email. And you can send me and drop me an email with your questions, with your suggestions, and in case you want to do experiments together, we can arrange them. We cannot pay your travel, but we can host you in our laboratories. So please write down my email, take it with you. I'm in LinkedIn also, so you can contact me in LinkedIn in the future. And happy to work together if there will be the possibility. And please stay tuned on the activities of the optical sensor clusters of the IEEE Sensors Council, because there are schools that are organized not only webinars, also summer schools, winter schools, events. And we are welcoming students, researchers. Professor Carlos Ruiz Damarreno is very much active, so is very much, let's say, it's a big family of sensing people, not only optical sensing people, not only spectroscopy, optical sensors as a whole. Okay.
Yeah, that's correct. Yeah, thank you for sharing your email. Yeah, John Maida saying thanks you, Anna. Yeah, thank you very much. Yeah. And then,
Okay.
yeah, if you have any questions, yeah, you can directly reach out to Dr. Anna because she shared her email, any collaborations or anything, any questions. Yeah. Yeah, thank you. Yeah, we're at the time. Yeah, thank you very much, Dr. Anna. I appreciate your time. And that was a great talk. Thank you very much.
I see a very good friend connected. John Maida is a good friend since, I would say, 30 or 40 years. So my greetings. Hope to see you live somewhere, maybe to some SPIE conference or somewhere in Europe. Thanks
Yeah.
again.
Thank you. Yeah, have a good weekend all. Thank you. Bye-bye.
Thank you. Bye-bye. Bye.
Thanks.